Thank you for joining us, everyone. My name is Dana Robertson. I'm an associate civil engineer with Los Angeles County Public Works, and I'm the current secretary of the ASCE Metropolitan Los Angeles branch. I'll be moderating the Q&A portion of this presentation. I just wanted to let everyone know that the meeting is being recorded, and a few other housekeeping items. Everyone should be on mute right now. In case you're not, please mute yourselves just so there's no background noise affecting the presentation. And also, anytime during the presentation, feel free to type in your questions into the Zoom chat, and we will be asking questions at the end, or you can also type in once the presentation's done, and based on the time we have, we will go through those questions and ask Amit. And with that, I would like to introduce Chris Shepard, our current MLAB president, to give a brief introduction.
Hi, good afternoon, everyone. Thank you, Dana. My name is Chris Shepard. I'm a senior civil engineer with Los Angeles County Public Works. And as Dana mentioned, I'm the current president of the Metropolitan Los Angeles branch. I'd like to thank you all for joining us for what I hope will be the first of just many technical presentations that we provide throughout the year. I'd like to start by giving you a few quick updates on MLAB activities. Unfortunately, due to the current COVID-19 pandemic, we've had to cancel our in-person annual awards banquet. However, we did issue a call for nominations and we've completed the awards process. So I'm happy to announce that we have a bunch of wonderful projects that we're awarding this year, as well as a bunch of individual civil engineers in the field who will be receiving awards. So we're putting together an awards video, which will highlight all those amazing individuals and projects. So keep an eye out for that on our website in the next month or so. We'll be posting that up there for all of you to enjoy and to see what's going on. I'd like to also say that if anyone here on this call is working on any projects that will be wrapping up in the next year or so, please consider submitting your projects for award next year during our award cycle. We typically call for nominations in April-May timeframe. And so any projects that are wrapping up, we'd love to hear about it. I know everyone's working on some amazing projects in the LA region, so it would be great to hear from you and hear about your projects and recognize them through our awards process. The next thing I wanted to mention lastly is that we've also issued a call for nominations for next year's MLAB board. We have a variety of open positions next year, and there's a lot of great opportunities to help out, whether it's in an officer position or as a committee chair. And so I'd encourage anyone who's interested in that to go to our website, ascemlab.org. Check it out. It's under the elections tab. And if you're interested, you can read more about all the different positions and what they entail, and then fill out a nomination form, and we'll be conducting nominations, and then after that, elections. The nominations close, I believe it's August 14th. So please submit your nominations, and we look forward to hearing from you. Also, if you're interested in just participating, maybe not leading a committee or being a board member, then please reach out to us through our email and let us know how you'd like to contribute. And we're happy to get in touch with you and find the best way for you to be more involved in the coming year. And we start our new year officially in October. So I look forward to hearing from you, and I look forward to some great events in this coming year and for another great year with ASCE MLAB. So with that, I'd like to introduce our speaker for today's presentation. Amit Josh is our speaker today. He's a bridge engineer at Caltrans Division of Engineering Services, Office of Bridge Design South, which serves the Southern California counties. He has 10 years of experience in structural design and construction of bridges here in California. He serves as a project engineer on various seismic retrofit, bridge widening, and replacement projects in the Los Angeles region. And he's also a part of the post-earthquake investigation team at Caltrans. Amit has a Master's of Science degree from the University of California, Davis in structural engineering, and a Bachelor of Science degree in civil engineering from the College of Engineering, Pune in India. He's also a very active member of ASCE, and he's the founder of the Los Angeles chapter of ASCE's Structural Engineering Institute within MLAB. So now I'd like to turn it over to Amit to tell you more about SEI and to provide us with a wonderful presentation on his bridge projects. Amit, take it away.
Thank you, Chris and Dana. Good afternoon, everyone. Thank you for joining today's presentation. It's a great pleasure to start the Structural Engineering Institute chapter here in Los Angeles. We have so many structural engineers, but we didn't have a SEI chapter. I always wanted to start an SEI chapter, and this year, like with the help of MLAB, I was able to get it started. And today we are going to have a first presentation, uh, and we'll have many more such useful and interesting presentations in the future. You are all welcome to send me an email if you have any questions, or if you want to get involved with SEI chapter, like please feel free to send me an email. You can check about our chapter more on our website. I have shared a link here. You can directly go to ASCE MLAB and look for SEI LA chapter. With this, I'll start with today's presentation. So today's topic is seismic retrofit of bridges in Los Angeles. Like Chris mentioned, I work for Caltrans as a bridge engineer, and I have been there for almost 10 years, and I have worked on several bridge replacements, widenings, and seismic retrofit projects. And like we always wonder that we don't have any active, like any recent earthquakes except for the Ridgecrest, and are we still continuing to do the seismic retrofit projects? Like even after like such a long time has passed after the previous earthquakes. And I just wanted to touch bases on what we do at Caltrans and how we decide on which bridges will be retrofitted and which bridges are not going to be retrofitted. And I happen to work on an interesting project in Los Angeles. So I'll share information about those projects with everyone. If you have any questions, please type in and I will try to answer all of them towards the end of the presentation. So the first major earthquake in the recent times, which happened in California, was 1971 San Fernando earthquake. And the result of this earthquake was, like every earthquake taught us something, and we improved our bridge design like step by step after every earthquake, after doing a lot of research. So based on 1971 earthquake, the main causes of failures observed in the bridge columns were lack of confinement, like lack of the hoops or the stirrups in columns. So that resulted in addition of confinement reinforcement, as you can see here in the slides. The next major earthquake which happened in California was 1989 Loma Prieta earthquake, which resulted in collapse of Bay Bridge and Cypress Viaduct. And the main issues which were brought into consideration during this earthquake was the support widths, especially the hinge support widths or at the abutments, and also the better structural framing and continuity for multi-span bridges. Another major earthquake which happened here in Los Angeles was 1994 Northridge earthquake, which resulted in collapse of like Route 5 and Route 14 interchange. This was the second time that this interchange had collapsed. Like I think it had collapsed also in 1971 earthquake, and it again collapsed. It was reconstructed, and it again collapsed in 1994. And this kind of brought into our attention the importance of balance stiffness and mass from bend to bend and from frame to frame, as you can see here in this picture. So, yeah, this picture explains more clearly. So basically, when we are designing new bridges nowadays, we need to balance the stiffness between the columns, adjacent columns within the bend, and adjacent bends within the frame. This is an extremely important point which we learned from 1994 earthquake. So what is Caltrans Seismic Retrofit Program? This is an ongoing program, and each earthquake has taught us something new. And at Caltrans, we have tried to incorporate those things into our bridge design. So in 1971, it was like we started providing more confinement. 1975, we started using cable restrainer units. Then 1989, we again started providing more confinement and using pipe seat extenders. Then again, also the seat widths, the criteria for at least minimum 24-inch seat widths came into picture. 94 earthquake taught us about mass and stiffness balances between adjacent columns and each frames between the like continuous bridges. Approximately around 2,000 bridges have been retrofitted in the past at the cost of $12.262 billion, which is a huge amount. Like when we are driving on the freeway, like we don't really realize like how many bridges we cross, especially here in LA, like where we have to commute so much. Then what is the need for seismic retrofitting? Like why are we still seismically retrofitting the bridges? The first and important thing is that the past earthquakes, they dictate the need for seismic retrofitting, like how the bridges have performed in the past. Maybe some elements got damaged, so that's why we need to fix them. Secondly, like I think bit after like 1989 earthquake during phase one and phase two retrofit program, more than 2,000 bridges were retrofitted, including single column bend bridges, multi-column bend bridges, and every year we additionally retrofit around 30 plus or minus bridges through widenings and new screenings. So the reason why we need to retrofit is so that because our standards are currently like constantly evolving, and as we move forward, we need to make sure that the existing structures they are aging as well. They are capable of handling the loads from an earthquake. Some of the challenges in seismic retrofit programs or in projects is the need to identify the design scope early on. Usually, like in normal projects, we identify the exact scope when we go into the actual design phase. But for seismic retrofit projects, we need to define the scope well before the actual project starts so that we have the allocated funding for the work which we need to perform. Then widening of the existing bridges again pose a challenge because now based on the new memos to designers, I think 20-15, we need to check if the existing bridge is capable of handling all the seismic forces on its own before we widen that bridge, which is something new which Caltrans has introduced. Seismic hazard maps are constantly changing. USGS is updating the maps, and the trend is moving towards like a new modern seismic hazard maps. So because of that, maybe some areas which were seismically like not severe are now becoming more seismically active. So we need to constantly rescreen the bridges in California and identify which bridge needs to be retrofitted. So how do we screen the bridges for seismic retrofitting here at Caltrans? Is mainly like these are some of the like list of like few items which we consider. Like the first is if the bridge has the potential for liquefaction and lateral spreading. If the soil, the foundation is will be affected by liquefaction. Then second one like seat widths and cable restrainers. In the past, even though cable restrainers are effective, but if they are grouted, they become like extremely non-effective. They are only effective like 10%. So that's a major concern which was brought into our attention. Then bridges which are crossing active faults, bridges which have increased ground shaking hazards due to updated USGS maps and information, then improvements in seismology, seismic analysis techniques, and bridge retrofit needs, then bridge vulnerabilities not addressed in the previous programs. So for this screening, which happened like a couple of years back, initially, I think 13,000 bridges were screened, and out of 13,000, 500, approximately 500 structures were identified to be potentially vulnerable to hazards and structural vulnerabilities. under an earthquake. Now coming to like that was the basic like how we screen the bridges for seismic retrofit. Now coming to the actual retrofit part, like how do we actually retrofit the bridges? There are like multiple ways, and like it is also unique to a bridge, like how the bridge is, how old the bridge is, the as-built plans. Like there are so many factors which dictate what retrofit strategy you are going to use. It is like a team of engineers work together to come up with the right strategy for retrofitting. It is not just one person's opinion, like geotech engineers, earthquake engineers, hydraulics, then district engineers, roadway maintenance engineers. So like a team of maybe around 20 to 50 people approximately, depending on the scope of the project and how many bridges are involved, will work together to come up with the retrofit strategy. The main principles or the main things which we do in retrofitting the bridges is to reduce mass, then reduce substructure, to retrofit by substructure replacement or additions like adding new foundations, then separating the mass. Column encasing is common, hinge modification, like installing cable restrainers or pipe seat extenders, then doing interim retrofits, like until a new bridge is constructed, doing like a temporary retrofit or retrofit by replacement. The main reference guidelines which we use for seismic retrofit are Caltrans Seismic Design Criteria 2.0 and Memos to Designers 20-4. Here is like an example of a Greenville Bridge, which was built in 1922. And this bridge was retrofitted by reducing mass. As you can see in the picture on the right side, that the bridge deck was originally the bridge deck consisted of a heavy concrete, like thick deck. And on the left side, you can see the finished product. So the original deck was removed and it was replaced with a lightweight concrete. This considerably reduced the demand on the bridge. And this is another example in the Bay Area where, like you can see, there's like a two-level bridge, and it was initially connected. So an additional column was installed, and these two structures were separated. So this is by separating mass. This is another example of column casing. Typically, we see like steel column casings, but this is a unique precast concrete column casing, as you can see. This was again in the Bay Area. Nowadays, we also use fiber reinforced polymer column casing. That is also proven to be very effective. Hinge modifications. Basically, for hinge modifications, we install pipe seat extenders where like the olden bridge have hinge seat widths which are very small, about 6 inch to 12 inch, and the longitudinal demands on the bridge are pretty much like higher. So in that case, we want to prevent the hinge from unseating. Like unseating of hinges has resulted in a lot of collapses in the past. So the main principle for installing pipe seat extender is that the pipes will hold the two parts of the frames or the superstructure together in case of an earthquake. So that was like a general introduction on what we do for seismic retrofit, like what are the basic seismic retrofit strategies. I'll talk about the projects which I'm working on, like the bridges which I'm currently working as a bridge engineer doing seismic retrofit. One thing what we look at when we are doing the seismic retrofit is that we need to make sure that the demands on the bridge, the displacement demands, are less than the capacities, which means that the main principle is to increase the capacity of the bridge elements. And like I shared with you, like that can be done by any of these techniques. So we want to increase the capacities and try to reduce the demands. First, I'll talk about Gaffy Street Bridge. Uh, Maybe many of you must have driven on Gaffy Street Bridge. This is an old structure. I don't know if you guys have noticed it. It's located by San Pedro, where we exit off 110 and turn on to Gaffy Street. So that's like the first intersection, or the first by the San Pedro sign, which you see. This is the first bridge, like you can see here in this picture. Uh, like this bridge is extremely old. It was built in 1935, and it has been said to be an historic bridge. Uh, that's why like it is extremely critical to to retrofit this bridge, and also it is important to not change its appearance because it is an historic bridge. So this bridge, like to summarize about the bridge, this bridge is like a three-span reinforced concrete T-beam girder bridge, where Pier 1 and Pier 2 consists of like 7 columns, and it is supported on pile foundation. Then abutment 1 and 2 are seat-type abutments, and then at the top of the bridge, there is like a AC deck overlay, and each span is simply supported. Like the spans are not continuous in this case, and they have rocker bearings or expansion joints at abutments 1 and 2 and at Pier 2. So this is kind of different what we see these days. Like most of the bridges in California are continuous span or simply supported or continuous span. But this is like a multi-span simply supported bridge, as you can see from the aspects. In the geology and foundation wise, this bridge is located in a pretty decent soil condition. So it did not have any liquefaction or lateral spreading potential. That was a good thing. The other thing was that the foundation piles were only 40-ton piles. So 40 ton is like 80 kips capacity. And on the wing walls are supported on wooden piles with only 20-ton capacity. So the main principle for analysis, or the main material properties which we used for analysis based on our Caltrans memos to designer 20-4 guidelines are like reinforcing steel Fy is equal to 48,000 psi, concrete is around 5,000, then the compression capacity of the piles is 40 ton. The tensile capacity of these piles is 0. They cannot handle any tension because these piles, like they are only like 16 feet in length. Like so you can see that they are not like deeply embedded in the ground. So I created a CSI bridge model. I'm sure like a lot of bridge engineers here use CSI bridge. It is very interesting to play with CSI, and the unique things in creating this model was creating the like the simply supported spans and creating the expansion joints at Pier 2, which was kind of unique, like by using a gap element. Uh, so using this model, I performed response spectrum analysis to get the displacement demands. And based on the SDC 2.0 criteria, I calculated the capacities for these pier columns. We had to make some like assumptions in order to model this bridge, because like it is the piers are not exactly a pure wall since they have openings in between. So it's not exactly a pure wall. So it's I modeled it as individual columns. So the ductility demand here was calculated as displacement demand over yield displacement capacity. And this ductility demand is compared with this chart from Memos to Designer 20-4. So in Caltrans, they did a lot of research with universities, and based on their research findings, they came up with this table, which kind of tells you what is the maximum allowable ductility capacity, mu C max. So our mu D has to be less than mu C max. In that case, you don't need any seismic retrofit. But Well, I'll talk about my results further. This is the longitudinal model, as I explained earlier, where we have an expansion joint in the middle, and this is the transverse model. Yeah, so the displacement demands, you can see that in the transverse direction, it will act like a shear wall, so it is pretty good. So we don't need any retrofit in the transverse, but in the longitudinal direction, you can see that the ductility demand ratio, it exceeds the capacity. So we have to retrofit these columns. Another thing I forgot to mention about this bridge was the quality of the as-built plans. Since this bridge was constructed in 1935, the quality of the as-built plans is very poor. So it was a challenge to identify what type of reinforcement has gone into it, what are the dimensions of the piers. It was extremely challenging and also interesting. But yeah, since this is an older bridge, these days, we do not allow any longitudinal splicing, but like there are some splicing here at the bottom of these piers. I don't know if you can see here in this drawing, but there is like these vertical rebars are spliced, and again, like the confinement, like the confining reinforcement is also very negligible. Like number 4 is at 18 inches. This is the picture of the pier walls. You can see that it has like 1 foot tall proper bearings at the middle pier. These are the piles which I mentioned earlier on during my presentation. And given the geometry of the pier walls, it is extremely difficult to install the steel casing. So we had to come up with a different type of strategy to confine the columns. And so we decided to install fiber reinforced polymer casing. And we are also going to install the carbon fiber anchors to hold this casing in place. Initially, we were also planning on installing the casing on the outer columns, but since this is an historic bridge, these outer columns have uh, architectural treatments, and it was not allowed to change the look of the bridge. So after doing exhaustive calculations, we were able to determine that just providing the casing on the interior columns, we can still strengthen the bridge and prevent it from collapse. The main idea behind seismic retrofit is from preventing the collapse mechanism from forming. That is preventing plastic hinging from forming. Luckily, the PGA at this site is not that great. It is around 0.58. So it's not like a very high ground motion susceptible site. Another important aspect we had to consider was in our retrofit strategy was the 1 foot tall rocker bearings. Like 1 foot is like a pretty considerable amount of thickness. So in case of like a longitudinal movement of the bridge, chances are that the spans are going to get unseated and the bridge will get unseated from the rocker bearings. So another alternative was to construct the catcher blocks, so even if the spans slide on the rocker bearing and then they will fall on these catcher blocks instead of falling 1 foot, which will create like huge damage. So like after doing all these analysis and brainstorming what retrofit ideas we are going to do, everything comes down to a price, like how much it is going to cost. So approximate cost which we calculated was around like $800,000. Like this project is still ongoing and we are still going on with the final design. So this cost may change. But like we want to do like the main thing is like we want to do bare minimum possible work to get maximum output or maximum uh, like uh, what like maximum outcome out of our retrofitting. That's the main strategy what we implement in seismic retrofitting. So the next bridge I'll talk about is Compton Creek Bridge overhead. Uh, so all these three bridges I'm talking about, they're part of the single project. This bridge is located on Route 91, and it's a pretty like a multi-span bridge, pretty long, and it is like it has Compton Creek which passes underneath it. So that has like unique challenges to us. So just to give a little background about this bridge, that it was built in 1974 and it was originally retrofitted in 1996. But again, like as I explained earlier, that we have come up with new screening criteria, and this bridge was again re-screened by Office of Earthquake Engineering for seismic retrofitting. So we had to do. So I reanalyzed this bridge mainly. So this bridge consists of like left and right bridge. Like if you look at the picture, you won't see that there are two bridges, but the left and right side of the bridge are separate. They are separated by a longitudinal joint. These days, we don't have these kind of longitudinal joints because they become a maintenance issue. But since it was constructed back in 74, we have the longitudinal joint. It is an 11 span bridge. On the left side and 10 spans on the right side. Last two spans are pre-stressed concrete, and the remaining spans are cast in place, just regular reinforced concrete. In 1996, they had retrofitted all the bends except for bend 2, 3, and bend 4. Here is like a general plan view of the bridge. You can see that like these bends are uniquely like placed. They have skew of like around 40 degrees, like bend abutment 1, bend 2, bend 3, hinge 3, and then from there on, from bend, and bend 5 is only on the left bridge. It doesn't extend on the right side of the bridge. Then bend 6, bend 7, like the skew changes. So it was very interesting and very challenging to model this in CSI Bridge. Here is like the rest of the bridge. I could only show half of it here. The remaining part of the bridge is here. You can see that like from bend 7, bend 8 onwards, it becomes like the skew is almost zero. So, and hinge 10 is also like no skew. And then bend 11 and abutment 12 have certain amount of skew. Another thing is that this bridge branches off, and there's another bridge which kind of connects to this main bridge at bend 6, which is the off-ramp bridge, and it branches off from the off-ramp bridge. So up until bend 6, this off-ramp bridge is also supported by this main structure. There were a lot of complications in modeling this one. And again, here you can see on the next slide that there is another on-ramp bridge which kind of joins this bridge at bend 11. Geology and foundation wise, this site mainly consists of medium dense silty sand. Originally, this bridge was found out to be to have a potential for liquefaction and lateral spreading. So we did like in-depth geotechnical investigations, and based on the current standards, Geotech did the liquefaction and lateral spreading analysis, and it was concluded that the potential is negligible, so we don't need to retrofit the foundation for liquefaction and lateral spreading based on the analysis. It took almost a year just to do the geotechnical investigations and analyses. Uh, Both the abutments and all the bend columns are supported on class 70 driven concrete piles, like 70 ton, that's 140 kips. Again, the material properties, since this is kind of like a newer bridge as compared to the Gaffy Street, you can see that the steel which is there in the existing bridge has the yield strength of 66 psi, and concrete again 5,000 psi. All the columns are fixed at top and pinned at bottom. So in order to analyze this bridge, I modeled it. This is the model. I'll talk about the model. I modeled it using CSI Bridge. And along this blue line, which is the central line, I had to place like an expansion, like a gap element to allow that, since there is an expansion joint between each bend. So that was very intricate and challenging to do. It took me some time to generate this model. Like, it is extremely important to have a realistic model of the bridge, because if there are any errors in the model, you may be underestimating the capacities or overestimating the capacities of the bridge. So it is at Caltrans, like, it is extremely important for us to have an accurate model, or and then we support it by independent checks and hand calculations to get a good idea about our model and not just rely on the computer. So a response spectrum analysis is a typical analysis which we use to perform to calculate the seismic demands. It's basically like a lump mass, and when you move it, uh, how much is the response based on the ground shaking. That's how you calculate the response spectrum. I mean, the displacement demands using response spectrum analysis. And to calculate the capacities, we had to do a pushover analysis on each bend. So we did pushover analyses on all like 10 bends, and there are, I think, 4 frames. So we had to do pushover on each frame in the longitudinal direction. So there were like multiple pushovers to calculate the capacities. Again, the criteria was to compare the ductility demand with the allowable ductility capacity, that is 3 in this case, because these columns are slightly better, or like much better, actually speaking, much better than what I showed you for Gaffy Street. So based on my analysis, I found out that the hinge 3 and hinge 6 have demands of around 20 inches, and the hinge seat widths are only 15-inch wide, which means that in case of an earthquake, like these 2 frames, if they move in the opposite direction, the chances are that they are going to separate, and they're like the frame which is sitting on the other frame is going to fall off. So the strategy here was to install pipe seat extenders at hinge 3 and hinge 6. Hinge 10 was good, like the capacity, the demand was less than the hinge seat width, so we didn't have to do anything there. You can see like these are the old hinge details for hinge 3 and 6, and this is for hinge 10. The 7 inches and 8 inches of uh, uh, of hinge seat, and here this other hinge is like around 24 inches, 2 feet wide. Nowadays, like when we construct new bridges, the minimum hinge seat criteria is 30 inches based on SDC 2.0, and SDC 1.7 had a criteria of, I believe, 24 inches. Or it also depends on, that's not the ultimate criteria, but that's the minimum criteria. And the hinge seats are also dictated by how much longitudinal displacements you are anticipating at your structure, plus the thermal movements and any other like shrinkage or due to pre-stressing. So all these things come into picture when we calculate the hinge seat widths, like based on our current standards. So the retrofit strategy is to install pipe seat extenders. So installing pipe seat extenders is extremely challenging because you have to go from underneath. Like I'll go on to the next slide. You have to basically go at the location where there is hinge. Now in this case, we have railroad right above, right below our hinge location. So you have to create soffit openings from both sides to go inside the cell and then put in this pipe, like drill across the hinge and avoid any reinforcement and anything which may be there, and drill these pipes in and then construct these bolsters at both the ends to secure these pipes in properly. So it is a very cumbersome job, but it needs to be done to ensure that this bridge is safe. And yeah. The second thing was after earlier I mentioned that we also did pushover analyses on the uh, on our bridge bends. So based on the pushover analysis, it was found out that these bend 2, bend 3, and bend 4, which were not retrofitted in the past, as you can see here, the demands were greater than the capacities, which means that they needed to be retrofitted. I'm not sure like why they did not retrofit these bends. Maybe because of the creek which was present here back in the past. But it clearly indicated that we had to retrofit these bends based on our analysis results. So it was proposed to install like a regular standard steel casing. Uh, uh, so installing steel casing bumps up the capacity, like allowable capacity values to 8 instead of 3 without any casing. So installing the casing is basically going to give it more ductility. Like so, in case of a strong earthquake, these columns will behave like they will have more ductility. They can displace more and not just like the plastic hinging will be delayed, and that will give them more capacity. Like the main goal in seismic retrofit is that we want to prevent any sudden failures. So even if the bridge may be rendered, say, like useless after the earthquake, but we don't want any collapse during the earthquake because that causes like excessive damage and especially to the traveling public, it's a catastrophe. So you can see here, like these are the bent columns, which we are going to retrofit by installing column casing. And another unique thing is like these two bends are uh, within the Compton Creek area. So we have to go excavate, do some water diversion, get permits from the concerned parties, and also for installing the pipe seat extenders, we have to work with railroad companies. This is like a like typical section views how the column casings are going to be installed. The cost for this project is significantly higher because of the huge, like because this bridge itself is huge, and the amount of work which we are doing is pretty enormous. So it's around 4.8 million. This may change because we are still in the actual design phase, uh, and as we move on, I think it will definitely change a little bit, not drastically, but yeah, it will be interesting to know. So like I mentioned earlier, the construction issues are creating access openings above the railroad. As you can see here, there like railroads, which is going all like right under this hinge location. Then again, we have a creek here, like Hinge 10. Like luckily we eliminated work at Hinge 10, but Hinge 10 also has another like a flood control channel. And it becomes a huge challenge to work above any water bodies. We need to get so many permits and we have to prevent debris from falling inside. The third bridge, which I'm working on, is Harbor Scenic Drive Bridge. This bridge is also very interesting structurally, and I'll share with you guys shortly. This is located at around the Long Beach port area, and this area has a soil which is prone to liquefaction and lateral spreading. So we had to do a lot of geotechnical investigations here. So originally, this bridge actually belonged to, I think, Port of LA, and it was relinquished to Caltrans probably sometime in like 80s or early 90s. So they had retrofitted this bridge in 94 by installing partial height casings and full height casings, and the foundations of some of the columns were retrofitted by installing like a top reinforcement mat for 16 columns. The soil mainly consists of like soft silt with interbeds of clay. And like I mentioned, this had a potential for liquefaction. So Geotechnical, again, geotechnical investigations took almost a year. And after their investigations and lateral spreading analysis and liquefaction analysis, a team of engineers like we decided that the potential exists, but it is negligible, and it is not significantly, it won't significantly damage the bridge. So the piles are embedded deep enough, they penetrate below the liquefiable, the layers of soil. So which was a good thing, and they would still retain enough capacity. Again, the material properties which we used for this bridge are 4800 kips, and concrete is 4500 psi. All columns at bends are fixed at top and pinned at bottom, and plastic hinge is expected to be formed at the top of the column. So let me talk about the model first. This is the CSI bridge model. So again, similarly, like we performed response spectrum analysis and pushover analysis on each of these on this model for this bridge. As you can see here, like the way these bends are oriented, it's like a jigsaw puzzle. And to model this thing in CSI bridge was extremely challenging. The main thing was to so we actually generated an Excel file with all the coordinates of each bridge column, and that's how we model it, not by using a direct interface which CSI Bridge offers. So we had to go the back route where we can just change the coordinates and put the elements and everything in Excel file and then extract our model. So this was an interesting task to do. And each column is different. Like as you can see here again in the column retrofit plan, this is like the original retrofit which they have done. You can see that some columns were retrofitted by installing partial casing. Some columns were retrofitted by installing full height casing, and some footings were retrofitted. So we had to go and change the structural properties for each and every column based on what kind of retrofit they had, like there has been done in the past, in order to realistically start modeling our bridge. So after we generated the model, which took considerable amount of time, of course, we did the response spectrum analysis, and on each of these bends, we had to do pushover analysis independently in the direction of the bend to calculate the demands. Sorry, to calculate the capacities. So again, since the columns which were retrofitted, the capacities for those were around 8, and the columns which were not retrofitted, the allowable ductility capacity for those were 3. So we had to do a lot of analysis. Another interesting thing which I forgot to mention in this model is if you look at bend 4 and bend 3, there are 2 hinges here. Originally, there was a railroad, like a railway route, which used to pass under these 2 bends. That's why like you have this separation here. You can see here these 2 bend 3 and bend 4. Same thing here, hinge 3 and hinge 4. So basically, there is just a small slab which rests on these hinges here, and it's bolted in by these bolts. So we found out like our displacement demands are pretty less than our capacity, like our hinge seats basically. So we don't need to do much retrofit. At hinge 8, they had previously retrofitted hinge 8 by installing strong pipes, like basically pipe seat extenders. And they had, I think, allowable displacement of around 8 inches. And our demand was around 12 inches. So it was decided that it's reasonable, even if worst case scenario, these pipes they won't completely break off, but the end plates may break off. So it was decided that we don't have to do any hinge retrofit, given that the original retrofit, which is there in place, is acting pretty good. So this is like a final plan view of this bridge. You can see here that so based on our analysis, like I mentioned, the lateral analysis and longitudinal, transverse and longitudinal analysis, we found out that these columns which I have circled, it's kind of hard to, I had like a 2-page table for each column at each bend in my final report. So we decided like which columns need to be retrofitted here using our analysis. And this is not just done by me, but like a team of engineers. I was the main project engineer, and a team of other engineers helped me to do this analysis. And each model is independently, or each bridge strategy is independently checked by another engineer, just to make sure that that the other person has not missed out anything. Especially in this kind of a complex bridge, it is extremely important that we consider that. At the end, it was decided to provide steel casing. So some of the columns were already partially encased. I don't think you can see it from here. And some of the columns were fully encased, and some columns were not at all encased. So it was decided to, let me see if I can, yeah, here you can see. So this is like, these are the columns which were partially encased, and these are the columns which were fully encased. So in our strategy, we decided based on our results to encase some of these columns which were not retrofitted in the past. And like we don't really do partial column encasing. I'm not sure like what was the idea when they did this, because this was not done by Caltrans. It was done by, I believe, LA County or LA City back then. Oh, another aspect of this bridge was that at the abutments, we have these 6-inch tall rocker bearings. For Gaffy Street, we had like 1-foot tall rocker bearings, but here they are like only 6-inch. But still, like the chances of the bridge deck like dropping off are considerably high. So we decided, and then the abutments here are not like a continuous abutment. They have like a pedestals. So we decided to have catcher blocks for these abutment seats as well, to prevent from sudden dropping by 6 inches. Because if you look at the total bridge deck, and like it's a huge mass of concrete, even if 6 inches looks really small, it's still a huge impact, and it can considerably damage the structure. The cost for retrofitting this bridge was around like $550,000. This may change a little bit depending on like actual final design. So the total cost estimate for this, like these 3 bridges, came to around like $6 million, which is which is pretty good. I think if you have to replace these bridges like individually, it will cost you like way more than 6 million. And these bridges are not that old that we need to replace them. So when we come up with a seismic retrofit like strategy, we have to do we have to have like a strong reasoning, like that why we want to retrofit it, can we replace it, and or if we don't want to retrofit and if we want to replace it, we need to be able to prove to the project manager or the funding authority that why we want to do that. For Gaffy Street Bridge, since it's an older bridge, but again it's an historic bridge, it would have been better if we replaced it. But again, there are so many clearances, like we couldn't justify why we need to replace it. Like if we can't justify that our retrofit strategy is going to prevent the bridge from collapse, we cannot go and just replace any bridge. So we have to first do every single possible thing, and if that is not possible, only then we go to replacing the bridge. Questions? I'm not sure how we are doing on time. Dana, do we have enough time?
So we are about time, but I think we can still squeeze in a couple of questions.
Sure.
So
Okay.
there were a couple of questions from Chris, and he said, when Caltrans does a retrofit, do you install any sensors on the bridge that can provide real-time data during an earthquake? And does Caltrans use any drones to assist with bridge inspections?
Oh, yes. So regarding the sensors, yeah, we usually install sensors on the new bridges to see how they perform, and also on some of, like, say, toll bridges, especially in the Bay Area, which are like unique bridges. Like we do when we did seismic retrofitting on those toll bridges, we definitely installed some sensors. And here also in LA, like some historic bridges, I know that we have installed sensors. I believe on Gaffy Street also we will install sensors to capture how much the bridge is going to displace. Yeah, we always like to do that. On one of my projects, like the text wash bridge replace in the desert on I-10, which happened like 5 years back, we installed a couple of sensors uh, to monitor the behavior of the bridge. And yeah, we have our drone, like we have multiple drones at Caltrans. We use the drones to survey the area when there was like a mud flow or like a mud slide a few years, like last year I think, or 2 years back in Montecito. We used our drone, especially if there are fires which are close to our structures or our freeways. We use the drones to survey that. Drones have, like, actually as a part of the PECWIT team, post earthquake investigation team, I am also learning how to operate drone, so that in case of an earthquake, if we have to go and do a site reconnaissance, then we can use the drones to actually see how much damage has occurred, and it gives you a realistic view of it.
So we had a couple more questions come in, so that will probably be it. Do you have any other programs that you use besides CSI Bridge to help with your analysis?
Yeah, so at Caltrans, we have a lot of inbuilt programs. We also have a couple of Excels which I have developed, and we also use M.ASCE, and we also have some other finite element programs like Abacus or Adena, which we use if we are doing like time history analysis or like in-depth other analyses, especially if we are dealing with arch bridges or cable stayed bridges or suspension bridges.
And for our last question, do you approach the retrofit of a bridge over a concrete channel different than a soft bottom channel?
Or a soft bottom channel. Uh, the retrofit strategy will not change, but from constructability point of view, we get in opinions from structure construction group to see how we can approach it. So in case of Compton Creek, it is not a concrete line channel. So we want to we don't want to disturb the natural channel, and we want to preserve it as much as possible. So when we are constructing or when we are doing any our excavations, and when we do our backfill, we will try to match the natural slopes, or we will backfill it with the natural material. So we take into account from construction point of view, not from the design point of view. Maybe sometimes design may change a little bit, but not drastically.
So I think that's all the time we have for questions. So thank you so much, Amit, for
I just want to add one thing to everyone. Like, thank you for participating in today's presentation. And I'm really excited that we have started this SEI Los Angeles chapter. If you guys have interesting projects which you have worked on, and if you want to share it with everyone, like, you're welcome to send me an email. And if you have any more questions regarding today's presentation, also, please feel free to send me an email. Sorry, I couldn't answer all of them, but it'll be great to interact with you guys. And yeah, I look forward to seeing you guys in a few other presentations soon. Thank you.